Welcome to this course on fibers and yarns. This is just one of 6 presentations in the series of carpet manufacturing. Other classes cover such topics as carpet construction, dye methods, carpet specification, carpet testing methods, and backing and finishing. Hope you enjoy this course. The course objectives for fibers and yarns are listed here. They include understanding how the fiber manufacturing process works, learn the benefits of various fibers, learn how yarns are processed, understand the characteristics of fibers and yarns and how to distinguish one from the other, and summarize reasons to specify for performance. Almost all carpet and rugs produced in the U.S. today are manufactured from one of 4 pile fibers listed here from the 2008 statistics. Nylon, of course, is the major fiber used in the carpet industry. Polypropylene or olefin, polyester, and wool are also used. Each fiber's variations affect its performance characteristics and its end use. Now, just for some vocabulary terms, filament. When you see the word filament, that means bulk continuous filament or long continuous strands of fiber. And then we also have staple. When you see that, staple means fiber that is composed of short pieces of fiber, about 7 inches long, which are spun together to create carpet yarn. Modifications of the fiber shape developed by individual fiber producers can alter fiber characteristics and performance within each generic type. Because fiber selection affects end-use performance, manufacturers are a valuable resource in determining the fiber most appropriate to the application and the budget. 99% of the total face fiber market for carpets is composed of synthetic fibers. Historically, wool was the most prevalent fiber in the carpet industry, but as the market exploded in the 1960s, synthetic fibers were developed that provided a long, quality product in a more affordable price range. All right. Now let's look at natural fibers like wool. Wool is a natural staple fiber. It's durable, resilient, and is noted for its luxury and performance because it is soft, has high bulk, and is available in many colors and patterns. Wool is a staple fiber because the fibers are shorn from sheep, like shown here, friendly sheep, in short quantities and then must be spun together. It is considered to have a luxurious hand. Wool is self-extinguishing when burned. It will char rather than melt or drip when exposed to fire. Because of its higher cost, wool is usually used as a decorative accent and in lower traffic areas. Wool and cotton are the predominant natural, both plant and animal, fibers used in carpet production. Cotton is seldom used for broadloom. Other natural fibers used in area rugs are cotton, sisal, jute, core, silk, and hemp. These are not used for broadloom carpets, which are 12 to 15 feet wide carpet. All right, now let's look at synthetic fibers. All synthetic fibers are extruded. Natural fibers are not extruded. Synthetic fibers are formed by a process in which molten polymer is extruded or forced through tiny holes in a spinneret or metal plate. After the filaments emerge from the spinneret, they are cooled, drawn, and texturized to add bulk and cover. Okay, let's look at the steps here. So the first step, we would have blended polymer and color pellets, solution dyed only. So we'll call this first step blended, the blended color pellets. Spinnerets, that's the metal plates, like this little picture showing here, with holes through which molten fiber is pressed. So we're going to put this down as the spinneret step. Okay. Thirdly, we have the cooling tower step. So we have to cool. Fourth, mechanical draw stretching of yarns. So we'll put mechanical stretching of the yarn. Okay, we have the texturing is the 5th step. Make sure I spell it right here. And the 6th step is the yarn take-up. That is where it's then wound into cones. Yarn take-up. From this point, yarns can be together for string or air entangled with threads. However, it is important to understand that step 6, the take-up, is not the step. All yarn will have applying and heat set step. This is the same as spun yarns. All right, this slide compares the synthetic nylon with synthetic olefin. Nylon is made into BCF or staple fibers, and it makes up 55% of all carpet-based fibers. Once again, if we haven't covered it, BCF refers to bulk continuous filament, and as I said, that makes up 55% of all the fibers. Nylon is the predominant fiber class and used in carpet in the commercial market, and a significant fiber class used in the residential market. Some of the reasons it is so popular is that it's durable and resilient and resistant to abrasion. Nylon is excellent in wearability, abrasion, resistance, and resilience. It's easily cleaned and can be stain resistant. Nylon fibers withstand the weight and movement of furniture and are generally good for all traffic areas. There are two types of nylon used in the carpet industry. Type 6, it's up here on the top, and 6.6. They each have unique physical and use properties. Nylon comes in a wide array of deniers, lusters, and cross sections that provide different performance attributes and is offered as white dyeable. Think about the coloration possibilities here, and solution dyed. Solution dyed nylon has excellent color fastness to light and crocking, atmospheric contaminants, and harsh cleaning chemicals, in addition to excellent color clarity. It is also offered by some manufacturers with inherent stain-resistant properties, providing excellent resistance to acid-based stains that can be often removed simply with water. Over on this side, we have the synthetic olefin, and that's also known as polypropylene. They are two different names, but they are the same thing. They're equal. Same fiber. Olefin is only available as solution-dyed BCF. Remember, BCF is bulk continuous fiber. Polypropylene is used where resistance to sunlight fading and chemicals is more important than durability to traffic. Olefin and polypropylene are both color fast, resist fading, generates low levels of static electricity, and is resistant to acid-based stains. Olefin features include its inherent and permanent resistance to water-based stains, and because of this moisture resistance, is the primary fiber for indoor-outdoor carpet. So moisture resistance is key here. Okay, polyester features include its luxurious soft hand, inherent and permanent stain resistance, and ability to produce bright colors. Other features include good abrasion resistance, fade resistance, and cleanability. Most of the stains can be removed with hot water extraction only. Now, what's up above here is PET, and that stands for polyethylene terephthalate, which manufactured by Carpet Miller Independent Fiber Extruder. And PET has historically been used in staple form, but polyester BCF has gained market share in residential products. Good resiliency and texture retention can be achieved with high twist PET yarns. Polyesters provide color clarity and color fastness. They can be piece dyed or solution dyed. Polyester is predominantly used in residential applications at this time. Environmental sustainability may be a strong attribute of the polyester value chain if derived from recycled bottles. So the environment might be something you want to consider with this. Now let's go on to synthetic triexta. In March of 2009, the Federal Trade Commission approved a new generic fiber subclass name and definition, which is triexta, made from PTT. So PTT stands for polytrimethylene terephthalate. Triexta is manufactured as a bulk continuous filament, a BCF, which can be manufactured by a carpet mill or independent fiber extruder. Triexta features include inherent and permanent stain resistance, ability to produce bright colors, good abrasion resistance, resistance to fading, cleanability, a luxurious soft hand, if you will, and texture retention. As a new fiber, its uses in markets are still to be determined, but entry point is residentially focused with this one. This diagram shows the processes for two different types of nylon fibers, the BCF fiber versus the staple fiber. Both begin by being extruded. Basically, they both start out the same way, but as you can see here, after extrusion, they go through different processing. BCF is produced in yarn form, long strands of fiber that form into yarn bundles. Then one or more processes are required. You have plying here, air entangling, twisting, and heat setting, which we'll talk about that later. Then the extruded product containing the proper number of filaments for the desired yarn thickness is wound directly onto take-up packages. Staple fiber, on this side, must undergo several processes in order to convert it into yarn ready for tufting. Staple fibers may be converted into spun yarns by textile yarn spinning processes. When staple fiber is produced, large bundles of fiber called tow are extruded. After a crimping process, the tow is cut into fiber lengths of 4 to 8 inches. Staple fiber is spun into yarn and requires 3 critical preparation steps. Blending is one of the steps, carding, and drafting. Prior to the spinning process, any fiber can be formed into spun fiber. Okay, the process for BCF is short and sweet. This explains the more involved process for the staple fiber. A little bit technical, but we'll just go through it fairly quickly. After fiber extrusion, post-treatments for staple fiber, including drying and annealing, which is a heating and cooling process, increase tensile strength and generally enhance the staple fiber's physical properties. The filament bundle then goes through a crimping or texturing process that converts straight filaments to ones with a repeating kinked, curled, or sawtooth configuration. The blending process, so we do have the blending process to start here, then mixes the staple fibers from different bales to ensure that the fibers intermingle in a way that yarn streaking will not occur in subsequent dyeing operations. Carding, so I'll write this word down here, carding, straightens the fibers and puts them in a continuous rope-like configuration. And then there's the drafting. Drafting has 3 main functions. It blends the fibers, it places them in parallel form, so parallel right next to each other. It continues to decrease the weight per unit length of the total fiber bundle to make it easy to spin into the final yarn. The yarn spinning process draws the sliver down to the desired yarn size and inserts some twist to hold it together. So that's the yarn spinning process. Then the yarn is plied and twisted for various effects. So we're going to end with plied and twisted. After twisting, the yarn is wound onto yarn cones in preparation for heat setting, which sets the yarn twist. We're going to go into twisting and heat setting in a little bit more detail.